Dear students, welcome to online classes conducted by Lyra English Medium School, Tuni. Let me introduce myself at first. I am Mr. B.J. Kiran Babu, working as a mathematics teacher in Lyra English Medium School, Tuni. Today, we are going to discuss Chapter 1 Real Numbers from Class 10th of Mathematics Paper 1. Dear students, let me ask some questions first. How many of them do you know? Please tell me answers. Are you ready? Right. Now, say, what is meant by natural numbers? Yes, natural numbers are represented by the letter n. They are starting from 1. Or else you would like to say as simply counting numbers are known as set of natural numbers. Of course, they are infinite numbers. You say, what is meant by set of whole numbers? Yes, very good. Sit down. The set of natural numbers along with the 0 are known as set of whole numbers, and they are represented by the letter W. Very good. Right? What is meant by set of integers? Yes. The set of whole numbers along with negative natural numbers is known as set of integers. They are represented by the letter Z. They are represented by Z. Next, who know what is meant by set of rational numbers? Yes? Please tell me the answer. Right. Yes. The numbers which can be expressed in the form of P by Q, and Q is not equal to 0, whereas P and Q are belonging to set of integers are known as set of rational numbers. See here, there is one more question you are going to face. Why do we represent a set of rational numbers with a letter Q? What is the reason? Yes? Do you know the answer? Yes, tell me. Yeah, there is another name for set of rational numbers, that is set of coefficient numbers. So due to this, set of rational numbers are represented by the letter Q. Very good. And last one is set of, I think you might have expected what question next I am going to ask. Yes, very good. What is that question? Right. What is meant by an irrational numbers? You? Good? Right. The numbers which are neither terminating nor non-terminating are known as irrational numbers. Or else the numbers which cannot be written in the form of P by Q are also known as irrational numbers, which was represented by the letter Q dash or S. So finally, you might have known what is the name of the first chapter in our 9th class level. Yes, set real numbers. Did anyone know what is the definition of set of real numbers? What I expect, the same. That is the correct answer. The set of rational numbers and irrational numbers put together is known as set of real numbers. The set of real numbers are represented by the letter R. Okay, listen. Flow chart of real number system. Real numbers, of course, which are represented by the letter R. Real numbers are divided into two parts. What are they? Rational numbers are coefficient numbers, which are represented by the letter Q. We know they are in the form of P by Q, where P and Q are belonging to set of integers and Q is not equals to 0. And the next one is irrational numbers. They are represented by the letter Q dash or S. These irrational numbers are divided into two parts. What are they? Algebraic irrational numbers, non-algebraic irrational numbers. Examples for algebraic irrational numbers are the familiar numbers, we know very well. Root 2, root 3, root 5, root 7, etc. and so on. It is nothing but square root values. And next, pi. It is a Greek letter. E for epsilon. Of course, we need not discuss about this. It comes for you in your further classes. So these two are the examples for non-algebraic irrational numbers. Let us go through the rational numbers. Rational numbers are divided into two parts. First one is set of integers, set of fractions. Set of integers are starting from minus infinity to plus infinity, means unknown values. Fractions. We know here types of fractions, like fractions, unlike fractions, etc. And again, set of integers are divided into two parts. What are they? Set of whole numbers, negative natural numbers. Set of whole numbers are represented by the letter W. They are starting from 0 until infinite values. And negative natural numbers are starting from negative infinite value to minus 1. And again, set of whole numbers are divided into two parts. What are they? Set of natural numbers and 0. Natural numbers are represented by the letter N. And again, if you want to divide the set of natural numbers into three parts, let us know the variations. Here, why I would like to separate one, why I am writing one separately means, which is neither prime nor a composite number. And from this we came to know 2, 3, 5, 7 and so on are the examples of prime numbers. Of course, we know very well the prime numbers. The numbers which have 1 and itself are the factors are known as prime numbers. And next, composite numbers. 4, 6, 8, 9, 10 and so on. These are the composite numbers. Why? Because they may have more than 2 factors. So after finishes the flow chart of real number system, I would like to ask a question from any one of you. So you might have learned about real numbers. Here any one of you can give me an example for set of real numbers. This is the problem we are facing. We are able to give an examples for set of natural numbers, set of whole numbers, set of integers and so on. But when I am asking a question, most of the students are unable to say an example for set of real numbers. So to give a clarity, I would like to take one general example. Let us say, yesterday I went to market to buy some requirements to my family. After some time, I have completed my purchase. When I comes out from the market, unfortunately, I met my friend outside. He asked me, Mr. Kiran, what did you purchase in the bank? Should I say, my dear friend, see, I have purchased some onions, some beetroot, some carrot, some potatoes, some tomatoes. Is it necessary to say all these things? What did I purchase? No. Can you are laughing. Yes, I came to know I need not to show all the things which I purchased from my basket. So simply I can say I have purchased vegetables. Even though my friend asked me, show me a vegetable, which did you purchase? I can show this one. Is it a vegetable or not? Yes, this is a vegetable. Or I may show carrot. This is a vegetable. So everything what I purchased from my basket, these all things comes under vegetables. So why can't you give an example for a set of real numbers from our flowchart? If you take either natural number or 0 or whole numbers or negative natural numbers, integers, fractions, rational numbers, algebraic irrational numbers, non-algebraic irrational numbers, whatever we wrote on this chart, everything comes under real numbers. Is it clear to all? Yes. These are all the examples for set of real numbers. Okay. Let us discuss about division equation. This is a familiar rule which we have studied in our previous classes. It is nothing but a divisibility rule, what we call divisibility rule in our previous classes. So the divisibility rule is dividend is equal to divisor into quotient plus remainder. Let me explain again. Dividend is equal to divisor into quotient plus remainder. You might have recollected. Yes, very good. Let us take one example. Here 14. 14 is nothing but dividend. This 14 I would like to divide with 4. Any one of you can say 4 divides 14 exactly? No. No. Because you know the fourth table very well. 4 ones are 4, 4 twos are 8, 4 threes are 12 and 4 fours are 16. So is it possible to take 4 fours are 16? No, it is not possible. So due to this, so the nearest value is 4 threes are 12. Right? 4 threes are 12. So from 14, if we subtract 12, what remainder do we get here? Yes, 2 is the remainder. And one thing here we notice, 14 is, don't show this arrow mark. Here this arrow mark represents an example actually. 14 is a dividend, the largest number. 4 is the divisor and 3 is the quotient. And finally we came to know 2 is the remainder. If we apply divisibility rule, it is nothing but division equation. In our class, let us leave that word divisibility rule. Let us know the new word, that is division equation. So what is the division equation? Dividend is equal to divisor into quotient plus remainder. If we apply this condition for the above division, in place of dividend, what can I write here? 4. Very good. What is the divisor from the division which was shown on the chart? 4 is a divisor. And what is the quotient here? 3, right? We wrote here. Plus instead of plus. And what is the remainder? Once you verify this divisibility rule, 4 3s are 12 plus 2 is nothing but 14. So this example, we changed it in terms of English alphabeticals by using lowercase letters. For example, instead of 14, I took a dividend A. How we took here 14 as dividend? In the same manner, I took A is the dividend. How we divide with 4? I want to divide with b. Means here b is known as what, divisor. Anyway, here we may get a coefficient. Yes, sir. Actually, we don't know where the value of a and b. So that is the case, we don't know what is the value of q also. So instead of coefficient, I am writing a lowercase letter q. When we multiply b and q, we get some product, Actually here, if you go through the example again, 4 3s are 12. We know that value. So that's why here we wrote clearly. But here we don't know what is the product of b and q without knowing a, b, q values. Let me assume the product of b and q is x. When we subtract x from a, we get some remainder. That remainder I represent with a lowercase letter r. How we wrote 14 is equal to 4 into 3 plus 2? By using division equation. If we apply the same condition for the second division, we observe, first of all, on left hand side, what we should write? We must write dividend. What is the dividend here? A is the dividend, b is divisor, q is quotient, and next plus we should add remainder. So this is the division equation. And next, the main important concept based on the division equation is Euclid's division lemma. Euclid's division lemma. Of course, you might have known Euclid, the name Euclid is familiar to you all because he wrote a book, The Elements, which we might have studied in our 9th class level as a third chapter. Yes or no? Yes. That person. Euclid's division lemma. Let us say, given two positive integers a and b, then there exists unique pair of integers q and r satisfying the condition what we wrote division equation here, the same condition we are writing here. A is equal to bq plus r, where 0 is less than or equal to r is less than b. Here I want to explain one example. Why can't we go to the same example? Let us see, if you take the same division, 14 is the dividend, 4 is the divisor. When 14 is divides with 4, the quotient is 3. 4 3s are 12, we know the product. When 12 is subtracted from 4, we get 2 is the remainder. Actually, we need to focus on this condition particularly. What is the reason? Here, can you say 4 divides 14 exactly? No, because 2 is the remainder. Let me explain one more example. Here 15 is there. 15 is the dividend. When I would like to divide this 15 with a divisor 3, yes, 3 5s are 15. 15 minus 15 is what? So 0 is the remainder. So from these examples we came to know sometimes when the divisor divides exactly the dividend, we get remainder 0. If the divisor is not a factor of dividend, we may get something as remainder like this example. So from these examples we came to know 0 is less than or equal to r, means remainder value, if divisor divides exactly the dividend, we came to know the remainder is 0, or else the remainder may be something. So from this we came to know 0 is less than or equal to r. But here one thing is clear, you see. Remainder is always less than the, b means what? B means what? Divisor. Remainder is always less than the divisor. Here what is the remainder? 2. What is the divisor? 4. 2 is less than 4 or not? In this example, what is the remainder? 0. What is the divisor? 3. 0 is less than 3 or not? Yes, the condition should applicable in this equation. So let us go through the definition again. Given two positive integers a and b, then there exists a unique pair of integers q and r. That means quotient and r also some integers satisfying the condition a equals to bq plus r, where 0 is less than or equal to r less than b. This is known as Euclid's division lemma. Okay, let us focus on applications of Euclid's division lemma. Let us say the first question, find the HCF. The full form of HCF is highest common factor, or else there is another particular word, greatest common divisor, what we call GCD in our previous classes. Find the HCF of 104 and 120. Actually, this Euclid's division lemma is useful to find out the HCF of two given numbers. Here, find the HCF of 104 and 128 by using the shortcut form of EDL is Euclid's division lemma. The process is familiar to you, which we might have done in our 8th class level. Let us go through the division. In between 104 and 128, what is the largest number? 128 is the largest number. So we consider 128 as the dividend. So automatically we consider 104 as divisor. And let us continue the division. 128 divided with 104. How many times? 104 ones are 104. Of course, this table is somewhat lengthy, but we can say the approximate value. 104 ones are 104. 2 times we cannot take. Why? Because 104 twos are 208. So it is too lengthy than 128. So let us subtract here. 4, 2. What is the remainder? 24 is the remainder. And now, we know this process will be continued until we get remainder 0. So again, we divide 104 with 24. That means this is the step 1 and this is the step 2. In step 2, remainder changes as divisor. In first step, divisor comes as dividend. Say 24 ones are 24, 24 twos are 48, 24 threes are 72, 24 fours are 96. So approximately 4 times it may possible. 24 fours are 96. So what is the remainder we left here? 8 is the remainder. So step 2 is also completed. And then, shall we continue the process? Yes. So again, the divisor 24 changes as dividend. Now, this dividend will be divided with the remainder. Now, 8 changes as a divisor. Can you say 8 how many times possible in 24? Let us recall the 8th table. 8 ones are 8, 8 twos are 16, 8 threes are 24. Right. 8 threes are 24. Did the division has been completed or not? Yes. The division is 1. See, when we are writing solution by using Euclid's division lemma to solve this question, actually we must do the rough work at first and later better you write the solution process. Here, let A is equal to 128, B is equal to 104. In step 1, by Euclid's division lemma, means it is nothing but we are writing the division equation. What we wrote, what we might have studied in Euclid's division lemma, A equals to BQ plus R. So A is what? 128. 128 is equal to BQ plus R. B is 104. If you observe, what is the coefficient in first step? 1 is the coefficient. BQ is lower. And then you would like to write a remainder 24. 24. And again we are writing, means again Euclid's division lemma will be applied for the step 2. Under how many steps? Until we get remainder 0, Euclid's division lemma will be applied in the same manner. Again you see, instead of 128, what can we write here? 104 is the dividend. 104 is equal to 24 into 4 plus 8. Here also we did not get a remainder 0. Now from this, the step 3 has been developed. So if we go to the step 3, 24 will be the dividend. Divisor is 8. Remainder is 3. And quotient is 3. Remainder is 0. We know very well, until we get remainder 0, the process will be continued. Under which division we get remainder 0, that division is known as highest common factor or greatest common divisor for the two given numbers. So from this we came to know these are all the divisors only. 104 is the divisor at first, 24 is the divisor in the second step, 8 is the divisor in the third step. That means under what division, wherever we get the remainder 0, that divisor is known as HCF of the two given numbers. So from this we came to know HCF of 104 and 128 is nothing but 8. Let us go to the second problem. Use Euclid's division lemma to show that any positive integer is of the form 6q plus 1 or 6q plus 3 or 6q plus 5, where q is an integer. So we are asking to show this condition. When we are writing this, at first we must write, don't forget to write Euclid's division lemma. Say what Euclid's division lemma says. A is equal to BQ plus R, where 0 is less than or equal to R less than B. Before going to write the first step, say A is equal to BQ plus R is there now. To take any one of the conditions from here, either 6q plus 1, 6q plus 3 or else 6q plus 5. If you want to take first one, 6q plus 1 or 6q plus 3 or 6q plus 5. Here one thing is clear. There is no variation for coefficient. In all the conditions, q, 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 which was only repeated. And if you observe carefully, from these three examples, we came to know the value of divisor. It is nothing but B value. B value is nothing but what you know? 6. But here, the remainders are changing. Is it clear or not? So from this, at first we want to write what is the value of B. let b is equal to 3. Now you continue the second step by applying this condition, Euclid's division lemma condition. A equals to, instead of b, in all conditions we came to know the value of b is 6. So can we write 6q plus r, where 0 is less than or equal to r is less than 6. Why? Because remainder is always less than the value of b. Means here we came to know the value of b is 6. So what should we expect the remainders? We should expect the remainders from 0, 0 onwards. Means 0, 1, 2, 3, 4, 5. So you take different remainders and let us substitute in this condition and continue the process. What will happen you will see. At r is equal to 0. If we substitute r is equal to 0, here you don't forget to write the possible remainders are. The possible remainders are 0, 1, 2, 3, 4, 5. So these remainders are possible. So at first we substitute r is equal to 0. What will happen you see. Here we are asking to show the positive of yes, listen. While substituting r is equal to 0, what is the value of a? Let us see. A equal to 6q plus 0. Now a is equal to what? 6q. May I write 6q as 2 into 3q? 2 into 3q. If we consider 3q as an integer, instead of 3m, I want to substitute, there is a value m. Now a is equal to, that value changes as 2m. Do we know the definition of even number? 2m, 2n, 2x, these are all the definitions of even numbers. So this is an even number. We are not asking to show as a 2m form. And next, at r is equal to 1, we substitute. What will happen you see. A is equal to 6 plus 1. From the above example, we came to know the value of 6q is what? Even. So in place of 6q, I am writing even plus 1. It changes as odd. It changes as odd. Let us take one example even number. 8 is an even number. Add 1, 8 plus 1. The result becomes an odd number. It is very simple logic. Right? May I go through the conditions, rest of the conditions? At r is equal to 2, a is 6q plus 2. May I split this 6q plus 2 as 6q plus 1 plus 1. Why I would like to split 6q plus 1 plus 1? 6q plus 1 is nothing but the above value. We came to know the value of 6q plus 1 is odd. So in place of 6q plus 1, may I write odd? Plus still 1 is there. When we add 1 to any odd number, it becomes even number. Now put r is equal to 3. Continue the Euclid's division lemma. A is equal to 6q plus 3. 6q plus 3. This is 6q plus 2 plus 1. Like that can be split. Why? Because 6q plus 2 is nothing but the previous step of the above. So we know the value of 6q plus 2 is even. So instead of 6q plus 2, may I write even plus 1. Now the result becomes odd. Now put r is equal to 4. And see what will happen the condition. A equals to 6q plus 4. This is 6q plus 3 plus 1. How did I split the above condition? In the same way, I would like to split like this. For what is the reason? Because we know the value of 6q plus 3. 6q plus 3 is nothing but an odd number. So instead of 6q plus 3, may I write odd. Odd plus 1 is nothing but even. Now, put r is equal to 5. And see what will happen. N is equal to 6q plus 5. From this and from this and this. From these three steps, you know how to split this condition. A is equal to 6q plus 4 plus 1. Because we know 6q plus 4 is what you know? Even. Even plus 1. The result becomes what? Odd. Under what conditions did we get odd number? Did we want to prove the conditions are even integers or odd integers? See, we want to show odd integers. So, where do we get odd integers? When we substitute remainder 0, we get even number. So, this is no use. When we substitute r is equal to 1, we get odd. Here we get. Here, when we substitute r is equal to 2, the result is even number. When we substitute r is equal to 3, we get an odd number. When we substitute r is equal to 4, we get an even number. And by substituting r is equal to 5, we get the value of 6q plus 5 is also odd number. So from these conditions, we came to know the conclusion. Therefore, the positive odd integer is of the form of 6q plus 1 or 6q plus 3 or 6q plus 5. Is it clear to all? Let us see. Use Euclid's division lemma to show that any positive odd integer is of the form of 6q plus 1 or 6q plus 3 or 6q plus 5. At first, what we would like to write? We would like to apply Euclid's division lemma. That is A equals to BQ plus R. You know the condition 0 is less than or equal to or less than B. Here, we came to know R value is, B value is 6. From this, the possible remainders are 0, 1, 2, 3, 4, 5. Here, one thing is clear, B is equal to 6. So, from this, we came to know the possible remainders are 0, 1, 2, 3, 4, 5. On substituting 0, 1, 2, 3, 4, 5 in different cases from this Euclid's division lemma equation, we came to know the different conditions. When we substitute r is equal to 0, we get an even number. When we substitute r is equal to 1, we get an odd number. When we substitute r is equal to 2, the result becomes an even number. Again, by substituting r is equal to 3, we get the condition is an odd number. By substituting r is equal to 4, we get the condition is an even number. By substituting r is equal to 5, the conclusion becomes odd number. Anyway, we are asking to show the general formations of odd numbers. From these conditions, where do we get odd numbers? You see, on substituting r is equal to 1, the value of 6q plus 1 is an odd number. On substituting r is equal to 3, the value of 6q plus 3 is an odd number. On substituting r is equal to 5, the value of 6q plus 5 is also an odd number. From this explanation, we came to know the conclusion. That is, the positive odd integer is of the form of 6q plus 1 or 6q plus 3 or 6q plus 5. Enough. Okay, dear children. So today we have discussed about division equation, Euclid distribution lemma, and applications of Euclid distribution lemma. That means we might have seen some problems based on Euclid distribution lemma. So today I am giving some homework based on today's explanation part. So the first one is find the highest common factor of 96 and 72. And second bit is from the first question 900 and 270. First question, in which way did I do the explanation? So before writing the solution, better you can go through the actual division process. Then you came to know how to write the sequential steps. It's clear to all, right? And second one is, you see, use Euclid's division lemma to show that any positive even integer is of the form 4q. In the above problem, we might have discussed that odd integer is of the form of 6q plus 1 or 6q plus 3 or 6q plus 5, etc. Here we are asking to show that the positive odd integer is of the form 4q, where q is an integer. So anyway, from this condition we came to know the value of b. B value is nothing but 4. So b value is 4 means we came to know what are the possible remainders. So the possible remainders are 0, 1, 2, 3. So the above problem, in which way did I write the solution? In the same manner we can go through the explanation. Then we came to know 4q will be the form of even numbers. So based on today's explanation, hope the useful part of the first exercise has been completed. That means the explanation of day 1 has been completed. So thanks a lot for this giving opportunity. Hope the next class, day 2, that is tomorrow, we will meet again and we will discuss the next topic. Thank you.